Hello everyone. So let us continue with the application part of the principal quantum number, because in the previous video we looked into the various principal quantum numbers. Okay, so let us now see how we can apply them. Okay, so this is a nice table. As you can see, it's taken from one of the book written by Puri and Sharma. Okay, so here this first column represents the principal quantum number, second column represents the azimuthal quantum number, third column represents the magnetic quantum number, and then the number of electrons that are possible in each of the orbital is what is calculated in the fourth and the fifth column. Okay, so let us look into each of them individually. So when we talk about the first energy shell, that is when n is equal to 1, okay, so if we talk about the number of electrons that can be accommodated in the n shell, it should be given by 2n square, which is nothing but equals to 2 into 1 square. That means the number of electrons that is possible in the first orbit should be 2. So let us see whether the concept of principal quantum numbers predict this correctly. So when n value is 1, we know that there is only one possible L value, and that is nothing but equals to 0. Okay, so that means you can write that particular subshell as 1s, because L value 0 means it is s orbital. Okay, so we will write that particular orbital as 1s. Okay, and the magnetic quantum numbers that are possible for them is only 0. One value is possible, that is 0. So that is why how many orbitals are present in the principal quantum number 1? Only one orbital is present, and that is nothing but 1s. So when we talked about the differences of the orbit and the orbital, I told you that each of the orbital, okay, can accommodate only 2 electrons. So since the first orbital has only one electron, one orbital present, that is 1s, therefore you can have only 2 electrons possible. Okay, so that is why the first principal quantum number can have only 2 electrons in total. Okay, let us look into the second energy shell, or the second principal quantum number equals to 2. Okay, so when value of n is 2, we can have two possible L values. One is 0 and the other is 1. Okay, so accordingly we can name these orbitals as 2s, because 0 means s orbital, so we can write that orbital as 2s. And when L value is 1, which represent the p orbital, we can write them as 2p. Okay, so we have in the second shell two possible values, which is 2s and 2p. Now let us see how many orbitals are possible. That is depending upon the m values. So when L value is 0, we can have only one possibility. So 2s would be only one orbital that is possible in the first case. Okay, let us look into the 2p orbital. Now, when L value is 1, there are three possible combinations, that is -1, 0, and +1. So that means three orbitals are possible when it is 2p, and it's given by 2px, comma 2py, comma 2pz. Okay, so there are three possible combinations when it is a 2p orbital. So that means that when it is 2p, that means three orbitals. So in total, the second orbital, the second principal quantum number, or the second energy shell, is having four possible orbitals. One orbital coming from the 2s, and three orbital coming from the 2p. So there are total 4 orbitals possible. So each of the orbital can accommodate 2 electrons. So the 2s can accommodate 2 electrons. The 2p can accommodate, since 2p consists of 3 orbitals, so each of the orbital can accommodate 2 electrons. Therefore, a total of 6 electrons is possible. So the principal energy shell with 2, n is equal to 2, can accommodate in total 8 electrons. Okay, that is also calculated from this particular formula 2n square, where 2 n value is 2, so n square, so it is nothing but 2 into 4, and that is equals to nothing but 8. Okay, so you easily understood that how we are able to calculate the number of electrons here. Now coming to 3, let us quickly go through it. When it is 3, you can have 3 possible L values. Okay, and correspondingly you can write them as 2s, 3p, and 3d. Okay, and let us calculate the number of orbitals. When it is 3s, only one orbital is possible. When it is 3p, there are 3 orbitals possible, because L can have 3 combination, that is -1, 0, +1. So there are 3 orbitals possible for 3p. When it is 3d, how many orbitals are possible? So d value is -2, so -2, -1, 0, +1, +2. So there are 5 possible combinations. So 5 orbitals are possible when it is 3d. So if we calculate the number of orbitals present in this particular quantum number, it is nothing but 1 plus 3, that is 4, 4 plus 5, that is 9 orbitals that are possible. So let us now calculate how many electrons are accommodated in each of these subshells. So when it is 3s subshell, we know only one orbital is possible, so it can accommodate only 2 electrons. When it is 3p, we know there are 3 orbitals possible, so that means a total of 6 electrons is possible, because each of the orbital can accommodate 2 electrons. Now further, when we look into the 3d subshell, there are 5 orbitals possible, so 5 into 2, 10 electrons total. So total of 18 electrons are possible in this particular subshell, and that is well calculated, understood from 2 into 3 square, that is nothing but equal to 2 into 9, and it is 18. Okay, so it is well explained by these principal quantum number. Please try to do this further. Fourth quantum number, and try to understand correspondingly how the number of total electrons that are possible is coming out to be 32. So I hope you understood how these principal quantum numbers are related to each other, and how we can calculate the number of orbitals present, and accordingly can calculate the number of possible electrons that each of the orbital can accommodate. So with this, I would like to close today's video. Have a nice day.